We're in Rosen, section 1.7, discrete mathematics and its applications and proof techniques. And I want to do a little bit of exposition on the relationship of proof by contradiction and proof by contraposition when it comes to proving implications. So we want to, so proof by contradiction of P implies Q. So we want to prove P implies Q, and remember its logical equivalence is not P or Q. And if we want to prove it by contradiction, we assume the negation of it. The negation of not P or Q is, by De Morgan's law, P and not Q. All right, so so basically, in order to do a proof by contradiction of an implication, we will continue to assume the same for the hypothesis, but we'll assume the opposite for the consequence, and we will assume them together. We're going to have an and there. Now, if we can show that not Q implies not P, then we conclude P and not P, which is a contradiction, it's a falsehood. So that means the negation of P implies Q led to a falsehood, and by contraposition, truth implies P implies Q, which is what we were trying to prove. But please note then that in order to show the negation of P from the negation of Q, if we did that, we actually did the proof by contraposition. This is equivalent to proof by contraposition. Now, we didn't have to conclude the negation of P and then compare it to P. We could have come up with a different contradiction, but it is pretty common that if we're going to prove an implication by contradiction, we will end up doing a proof by contraposition inside of it, as I have shown. Now, if on the other hand, we don't have an implication, say we want to prove R by contradiction. In this case, we want to assume the negation of R, and then we show negation of R implies falsehood. And then by contraposition, we can say that the equivalent statement is truth implies our original proposition, and we would be done. And in this case, we don't have a proof by contraposition, but we are leveraging contraposition to go from that statement there to the second statement there.